Hello and welcome to the second part of our 19th lecture of our course on photonic devices. On the first part we've discussed the threshold current and its dependence on temperature. Now on this part of the lecture we're going to talk about the effect of the confinement factor gamma on the gain condition, and we'll also discuss some other aspects of Fabry-Perot lasers and start talking about external cavity lasers, which in a sense can be an improvement on Fabry-Perot lasers, right? So let's start talking about the confinement factor. So in practice, the confinement factor gamma is a parameter that will vary between 0 and 1, and it will give us the fraction of the electromagnetic field which is effectively inside the active region, right? So how does this come about? Well, if you recall, in a Fabry-Perot type laser, or even in other types of lasers fabricated using double heterostructure, the active region, which is the green region here, will form a slab waveguide or even a 2D waveguide depending on the fabrication process. And these sorts of waveguides have transverse modes, right? So you could have the TE mode, fundamental and higher order modes as well. But in optical waveguides, as opposed to say microwave waveguides, only a fraction of the electromagnetic field is inside the core of the waveguide itself, right? So in optical waveguides and in optical fibers as well, if the core of the waveguide, the region with the higher refractive index, let's call it NC, and on either side you might have an N2 referring to the index of the cladding regions, right? In such a way that NC is greater than N2, but for such a waveguide, the transverse mode, will have a fraction of it which is not inside the core. This is called the evanescent field. So this fraction of the field, let's say that this is the electric field, right? Intensity, transverse electric field, for example. So you see that there's a fraction here which is effectively outside of the core of the waveguide. Now in the case of a laser, the core is also going to be the active layer. So this green region here is the active layer which has gain. Outside of this region, the gain should be non-existent. So only the field inside the active region, so only the fraction of the field which is inside the core, is going to contribute to gain. So effectively we're talking about this fraction of the field right here. Let's say it's 70%, so gamma in this case would be 0.7. So that's what gamma means, right? It's the fraction of the field that's effectively inside the core, and in our case inside the active region. And we can readily see that if before the condition for gain was that gamma was equal to the attenuation constant alpha, now if we said that only a fraction equals to gamma of the electromagnetic field, then we cannot use the gain coefficient itself here. We have to multiply it by uppercase gamma, which is the confinement factor, right? Because this will be the fraction of the field that's actually contributing to gain, and therefore instead of using gamma p here, we have to multiply it by gamma to take into account the fraction of the field which is actually interacting with the gain region, with the active region, right? The remaining part of the field is of no use with respect to gain. Therefore we need to take this into account, and this is the new condition for gain, right? When the confinement factor multiplied by the gain coefficient is equal to the losses, the cavity losses, then oscillation can start to occur. So this is a more accurate condition for gain. And if we substitute the gain coefficient, lowercase gamma, the peak gain coefficient, on the previous equation, we have this, right? Remember that we've discussed before that there's a linear relationship at the end of our previous lecture, I believe. Linear relationship between gamma p and the current, or the current density, or the excess carrier concentration. So this could be written in terms of either one of these, in such a way that gamma p is equal to alpha A, which is the attenuation constant associated with absorption in the active region, multiplied by J divided by the transparency current density minus 1. Okay, and this, you know, we could have used just as well I over IT, the transparent current itself, or also delta N over delta NT. All of these would be used instead of J over JT here. But since we want to express things as a function of the current density, let's use this and replace gamma p by all of this right here. So this is the new condition, and when it's satisfied, by definition, oscillation starts to occur. So the value of J that results from this equation will be the threshold current density by definition. So we can substitute J lowercase t here and isolate this current density, and this is what we'll find. And this is actually the threshold current density. Obviously, we could write that I lowercase t would be equal to I, the transparency current, multiplied by alpha divided by gamma times alpha A plus 1. Okay, and we would derive it in a similar manner. But we see here that the threshold current is equal to the transparency current multiplied by a term. And this term, in most cases, for most lasers, will result in the 1.1 that we have discussed. So that's why we've said that usually the threshold current, or the threshold current density, is equal to the transparency current, or current density, multiplied by 1.1, right? Now let's compare the line width in terms of wavelength for different types of light sources that we've seen and that we'll also see on our next lecture as well. For an LED, we looked at the line width of the LED on the lecture in which we've discussed it. And we said that the full width at half maximum was of the order of 20 to 40 nanometers, right? So a pretty broad line width. This is the corresponding line width in terms of frequency, so delta F would range between 2.6 and 5 terahertz corresponding to these wavelength values. So that's a pretty broad line width, right? And usually you don't define a wave guiding structure on most cases. So on this table here, the last column is showing the character of the laser, if it's multi-mode or single mode or single frequency laser. So this doesn't apply here. But then we saw the Fabry-Perot laser, and you know, in comparison, the line width of the Fabry-Perot laser is at least one order of magnitude smaller, right? And this is because, again, we're using a cavity, so the frequency response of the laser will have to take into account the transmittance of the cavity itself. And since it is a cavity, it's going to have a line width which depends on the quality factor of the cavity, right? Now, the Fabry-Perot laser usually relies on a cavity where the mirrors have a reflectance of around 30%. So that's not such a good cavity. The Q quality factor is not going to be so high, but already we see an improvement with respect to LEDs which do not use the cavity at all, right? So the line width is of the order of, you know, a few nanometers, so 2 to 3 nanometers. This corresponds to hundreds of gigahertz. But since the length of the cavity, so let's go back to the picture where we discussed the cavity. So the cavity is going to be the chip itself, right? And the mirrors are going to be the facets of the chip. So the mode propagating inside the active region, you know, will arrive at the facet and part of it will be reflected, and this is the cavity, right? So the mirrors on either side of the cavity are actually the facets of the chip itself. But the cavity length is the size of the chip, which is of the order of say 500 micrometers, half a millimeter. It's a pretty large cavity, and this will mean that the FSR is going to be pretty small, and for optical wavelengths the cavity is going to support many modes, many longitudinal modes. So even if you design the waveguide, right, the active region, the thickness and the width, to support only one transverse mode, the cavity itself will have many modes, because it's you know, a pretty long cavity. To see this, you can compare this length to the wavelength of light, which is of the order of let's say 0.5 micrometers, right, for visible light, and 1.5 micrometers for infrared. So around 1 micron is much smaller than 500 micron, right? And that's why the cavity is considered to be large. No doubt it will be a multi-mode cavity. So multi-mode for Fabry-Perot lasers. But there are other types of lasers, such as distributed feedback lasers, VCSELs, which use other types of cavity, which with different mirrors, multi-layer structure, Bragg reflectors and so on, for which the cavity can be made much smaller, right? And these we'll discuss on our next class about laser diodes. And for these, the line width delta lambda here, which is the full width at half maximum, can be made much smaller. So just to have an idea, can be made to be as low as 8 to 100 picometers, right? So that's 10 to the minus 12 meters. So here you see an improvement of 2 to 3 orders of magnitude. So you can make a light source which has a line width, spectral line width, that's much smaller. We could say that, talking about in terms of the color of light, the light emitted by the laser will have a much purer color, right? So because it will have a much smaller line width. And the correspondence here in terms of frequency, so the delta F, which corresponds to this delta lambda, will be of the order of hundreds of megahertz, so even smaller, to tenths of gigahertz, right? And because the cavity can be made smaller, so instead of having a cavity that spans for the length of the whole chip, you can make a very small cavity of the order of micrometers or sub-micrometers. Because of that, you can effectively make single mode lasers which will emit only one line, right, in the frequency spectrum. So just to have an idea of the importance of these parameters that are presented, the line widths and the modal characteristics that are on this table, we can recall the fact that the separation between different channels in a DWDM system is 0.4 nanometers, which is 50 gigahertz. So and therefore a question arises, which is what kinds of lasers could we use on such a system, right? Such a communication system. It's clear that we could not use an LED because the line width here is around 30 nanometers. So if the carriers corresponding to different channels would have such a great line width, they would clearly overlap. But even a Fabry-Perot laser wouldn't work here, right? So we would necessarily need to rely on more sophisticated types of cavities and lasers in order to implement such a system, because again, right, if the channel spacing in the frequency spectrum, let's talk in terms of wavelength, the separation between say two adjacent channels here is 0.4 nanometers, and if the line width is 2 nanometers, so you have a line width for the carrier corresponding to this channel, which is this, and then the line width of the carrier corresponding to this channel would be this, and you clearly see that they overlap. So the information on this channel you would have crosstalk and problems of this order. On the other hand, if we were to use narrower line width lasers, right, we could easily avoid this problem, because the spectral width of the carriers themselves, not taking into account the signal, but the line width of the carrier itself would be such that different channels do not overlap in terms of a spectrum. Okay, so and another important factor here is that in optical wavelengths, dispersion, in guided media such as optical fiber, especially optical fiber, is a prominent effect, right? So the signal can be distorted because of dispersion if light propagates over a span of kilometers of optical fiber, and the effects of dispersion rise with the line width of the signal. So certainly if you have signals that are being transmitted over a carrier which has a broader line width, the dispersion is going to be much greater. So in this respect as well, it's more desirable to use more sophisticated lasers with smaller line widths. Of course, this comes at a price, because these structures tend to be a little more expensive than simpler types of light sources such as LEDs and Fabry-Perot lasers. Their fabrication process is a little more involved, but for some communication systems this becomes a necessity. But another important aspect of Fabry-Perot lasers is related to the divergence angle, right? So we know that the spot size of a typical Fabry-Perot diode laser is approximately 8 by 2 micrometers, right? If we consider the light that's actually coming out of the output of the waveguide itself here, the mode, right? This would correspond to this dimension right here, because of lateral confinement, which can be, as we've discussed, achieved by gain guiding or index guiding. The typical width of the waveguide is going to be around 8 to 10 micrometers. So this is the lateral dimension, so that's why the 8 micrometers. And on the vertical direction you have guiding due to the active layer here having a greater index, but the mode actually, even though the active layer is typically a fraction of a micrometer, the mode for such small core waveguides will have an evanescent field which will extend beyond the core of the waveguide by a great length, and therefore this is why we have 2 micrometers on the vertical direction here. But this is just to give us an idea of the order of magnitude of the spot size of the light beam coming out of the waveguide itself. And of course, the smaller the confinement in any direction, the more diffraction the beam is gonna suffer, the greater the diffraction that will take place when the beam comes out of the waveguide, So we expect that in the vertical direction the beam is gonna diffract much more, because it's confined to a much smaller region in the vertical direction, and in the lateral direction we would not expect diffraction to be so great, because 8 micrometers is greater than 2. And this corresponds to what actually happened, right? The divergence angles are in the perpendicular direction, in the vertical direction, 30 degrees, whereas in the parallel direction, the horizontal direction, only 7 degrees typically, right? But lenses are usually used to collimate the light beam, due to this divergence, which will naturally occur once the light beam is ejected from the waveguide, because it's confined to such a small region, therefore diffraction cannot be avoided. This is illustrated here, right? We have the length of the cavity, which is typically of hundreds of micrometers for a Fabry-Perot cavity, but if the spot size is of this order, right, 5 to 15 micrometers, 0.1 to 2 micrometers in the vertical direction, we expect, as we've mentioned, the diffraction to be much more pronounced in the vertical axis. Therefore, this is why the beam is going to have a much greater divergence angle, so between 30 and 50 degrees in the vertical or perpendicular direction, and a much narrower divergence angle, 5 to 10 degrees in the parallel or horizontal direction. It's also the frequency-free spectral range, as we've discussed, is determining in terms of the number of modes that the cavity supports, right? So whether you have a multi-mode laser or a single mode or single frequency laser depends on the FSR of the cavity. And again, looking at this illustration here, we have typical values for Fabry-Perot lasers in which the facet is cleaved, the simplest kind of cavity that you can make. The length of the cavity varies between 250 and 500 micrometers, right? So around half a millimeter, the size of the chip itself. Now we can find the resonant frequencies, as we've discussed before, right, by using the condition for constructive interference. So basically what we're saying here is that beta times L, right, 2 times the length of the cavity is the length of propagation. Back and forth between either mirror light will propagate through a length which is equal 2 times L, the length of the cavity. If we multiply this by beta, the propagation constant, we find the phase shift which light goes through in propagating this distance, and this has to be a multiple of 2 pi. And if we substitute for lambda here in terms of the frequencies, and we isolate frequency here, we see that we have integer multiples of resonant frequencies given by this equation, which we've derived before. So m is a positive integer, and these are the resonant frequencies. So m times the speed of light in vacuum times 2 times the effective index of the mode times L. Now the effective index is a small number ranging between 2 and 3.5, right, for these types of waveguides. Actually, if we want to calculate the FSR is going to be the spacing between one resonant frequency, right? So let's say m equals to 3, and the adjacent or the next one m equals to 4. So what we can do is set m equals to m, and then set m equals to m plus 1, and then subtract the former from the latter, and we'll find that FSR is just going to be equal to this quantity right here, right? C divided by 2 and F times L. Now C is 3 times 10 to the 8th meters per second, speed of light in vacuum. This again is a number ranging between 1 and 3. And the length of the cavity, we can substitute 300 or 500 micrometers here. If we substitute 300 micrometers, which is the length of a Fabry-Perot cavity, we'll find that, this is 3 times 10 to the minus 4th. Speed of light in vacuum is 3 times 10 to the 8th. So we get 1 times 10 to the 8th, 412, divided by 5 or 6, we get a number which is close to 1.5 times 10 to the 11th. So this corresponds to what? 142 gigahertz, right? This is the FSR for a typical Fabry-Perot cavity. And for an FSR that's of this magnitude, so hundreds of gigahertz, the wavelength FXR is going to be 1 or 2 nanometers. And theoretically, we would like this to be much larger, in such a way that inside the gain region, which can span for tens of or hundreds of nanometers, we would have only one resonant frequency. So ideally we would like these resonant frequencies to be far apart in frequency in such a way that this FSR is much greater than what we're getting here for a Fabry-Perot cavity. So to obtain single mode lasers, single frequency lasers, the frequency FSR can be made much larger, again by making the cavity smaller, which can be seen considering that FSR is going to be equal to C divided by 2NF times L. If we can make L smaller, the frequency FSR will be automatically larger. Okay, so what we want to do is reduce the size of the cavity. And on our next lecture, we're going to discuss different types of cavities, different types of lasers, such as distributed feedback, double Bragg reflectors, vertical cavity surface emitting lasers, which use smaller cavities in order to attain larger FSRs, so that in such a way that inside the gain region we have a single longitudinal mode within that region. Right now we're going to discuss this last type of laser here, which is the external cavity laser. Okay, this is the simplest type of cavity, the external cavity, which can be used in order to obtain a single frequency laser. So but this requires an external cavity. So in order to achieve a single mode laser, it's necessary to guarantee that the losses of only one longitudinal mode are small. And one way of doing this, of course, is using the external cavity laser, which we'll discuss next. So on this type of laser, an ettalon, so a Fabry-Perot cavity with a fixed length, is used, and it has a large FSR because usually the cavity is made smaller. So typically the ettalon consists on a transparent substrate in which you just deposit typically higher refractive index film with a small thickness. So usually, sub-micrometer or 1 micron thick film, depending on of course the FSR that you want to design, but this is the cavity itself. Right, so you guarantee that the thickness here is of the order of the wavelength or sub-wavelength. So let's say that the thickness is 1 micron or so. And if light impinges on this type of film here, it's gonna suffer multiple reflections inside the film itself. So the surfaces of the film are gonna behave like a cavity, of course, but the length of the cavity, since it's the thickness of the film, can be made much smaller. So an ettalon is just this, right? Two parallel interfaces between different refractive index materials in such a way that you can make a cavity. So how can we use this in order to make an external cavity for a Fabry-Perot laser? Typically the configuration would be such as illustrated here. We would have the Fabry-Perot laser itself with the active region, double heterostructure, diode, forward biased, and the cleaved facets would form the internal cavity of the laser itself, just as we've discussed. Besides the internal cavity, the light that comes out of one facet is collimated using a lens and passes through an ettalon, which is illustrated here. Now you see that the ettalon is not exactly perpendicular to the beam, which is this, right? The beam is propagating here. So the ettalon is not perpendicular because this angle is used to control the resonant frequency, right? By varying the angle with respect to 90 degrees of this ettalon here, we can basically change the frequency or the wavelength of the resonant frequency, right? But so light passes through the cavity and is reflected by an additional mirror here. So you see that we have an external cavity, which is the ettalon itself. So the light is reflected by the mirror and then passes through the cavity again and then returns to the laser internal cavity. And therefore light is propagating through both cavities and suffering multiple reflections. Okay, does this make sense? So you have, in addition to the internal cavity of the laser, you have an external cavity, and this external cavity is the ettalon itself, right? Light is going to suffer multiple reflections inside this ettalon. And when talking about the frequency response of this laser here with this external cavity, now we need to take into account the transmittance of the ettalon, right? And the transmittance of the ettalon is going to look a lot like the transmittance of the Fabry-Perot cavity. So we'll have resonant frequencies in which the transmittance is close to 1, distanced apart by an FSR, just like in the laser cavity, except that since the length of the ettalon cavity is much smaller, the FSR is going to be made much greater. So as we've said before, the idea of using an external cavity is that we can make the loss profile to be small only for one particular mode of the internal cavity. Ideally the losses would be high for all of these adjacent modes here, and for a particular mode here the losses would drop. So the way that this is achieved using an external cavity is because the FSR of the ettalon, as we've said, because it's such a small cavity, is much greater. So if we look at the spectral response of the ettalon, it would look like this, right? The transmittance would be different than zero only at the resonant frequencies, okay? But these resonant frequencies would be much farther apart because the FFSR for an ettalon is much greater than for the internal cavity of the laser. Again, right, the FSR is inversely proportional to the length of the cavity, because the internal cavity of the Fabry-Perot laser is so large, the FSR is small. So if we look at the spectral response of that cavity, we have many modes within the gain region. But if we consider the spectral response of the ettalon, the FSR is so large that possibly, if you design it correctly, within the gain region, the region in which gain is greater than losses, you have only one longitudinal mode for the ettalon cavity, such as this one. And if you vary the angle, right, of the ettalon that we've discussed, so basically this angle theta right here with respect to the vertical direction, by varying this, note that you're varying the length of the cavity, the length of the ettalon itself, right? The ettalon is perpendicular, or theta is equal to 0, you have a smaller length. But if the angle is greater, then you see that the length of the cavity increases. So in this way you can control the length of the cavity, and this is gonna make it so that the resonant frequencies can be varied. The position of the resonant frequencies can be varied by controlling the angle of the ettalon, as illustrated here. So we can fine-tune it so that the resonant frequency of the ettalon coincides perfectly with one mode of the internal cavity. And of course, right, for these resonant frequencies, the transmittance of the ettalon cavity is equal to 1. So therefore, at this resonant frequency, what will happen is that the ettalon is going to be transparent. It's as if it were not even there, because transmittance is equal to 1, so light will pass through it and be reflected back into the cavity, and the losses will be close to 0. But outside of this resonant frequency, transmittance falls very fast to 0, therefore the cavity reflects all of the light, does not transmit the light that impinges on it, and for this reason the losses are greater, for frequencies different than the resonant frequency. Okay, so the laser will only emit light at this frequency corresponding to the resonant frequency of the ettalon cavity. Does this make sense? Okay, and because, again, right, because the length of the cavity is much smaller, because it's a thin film, the FSR is much greater, so you can have only one mode for which this that we have just discussed here, the loss profile, becomes smaller for this particular frequency. This will only happen for one single frequency inside the gain region, and the laser can be made to be a single frequency or single mode, single longitudinal mode of the cavity laser in this manner. Okay, so hopefully this makes sense. So we're basically using an external cavity, which is the ettalon here, in order to select one particular frequency in such a way that light coming out of the laser is a single frequency. Okay guys, so this was it for this lecture. We have discussed the first type of laser, which allows us to get a single frequency operation, which is the external cavity laser. On our next lecture, we're going to talk about other more sophisticated types of cavity which allow single frequency operation. Okay, so thanks very much for sticking around, and I'll see you on our next lecture.